Hi there, you're welcome to today's class. We are moving to the next section on motion. Meanwhile, I want to really tell you that he's not just a professor, but he's a medical student. And last time I was discussing with him, he said that this topic on equation of motion, JAMB precisely, that if you don't know it, you will not be able to solve some aspect of JAMB question. In fact, this topic is applicable to various aspects of JAMB question. Well, it's not me that said that. You listen to him, pay attention to what he's saying. He's no other person but Dr. Professor Izu Okoye Iman. Thank you, sir.
Okay. Good morning, all. Like you said, we're going to continue from equation of motion. The last time we gave an introduction to motion. I hope you've watched the video. If you've not, do well to go and see it so that we can be able to hit the ground running. Okay. Equations of motion, like I said earlier, we have different types of motion. So we're going to continue from equation of motion. Now, motion also can be classified under two categories. We have dynamics and kinematics. Now, when we talk about, let's look at it. Let's pin it down. Let's pin it down. We have dynamics, and then we have kinematics. We have dynamics, and then we have kinematics. Now, last class we talked about types of motion, and I said we have linear motion, and then we have another name for rectilinear motion is translational motion. And then I said we're going to talk about both the equation of motion and then the law of motion. We'll leave the law of motion for another day. We'll talk about the equation of motion for today. Now, what did I write on the board? I said motion can be classified or can be explained under two particular speed of study. We have dynamics and kinematics. Now, what is kinematic and what is dynamics? Now, both of them are the same thing. Kinematic is the study of motion. Dynamic is also the study of motion, but something is peculiar about the two of them. This is the study of motion with regardless to force. Now, this one is regardless to force. Regardless to force. Now, the study of motion with regardless to force is kinematic. While this one is the study of motion with regard to force. So, for what I'm trying to say is that kinematics talks about motion, but it does not specifically tell you what causes the body to move. It tells you how the body moves, but does not tell you what causes the body to move. But under dynamics, dynamics tells you how the body moves and what causes the body moves. In fact, most of the most emphasis we have on dynamics is that the force that causes the body to move is more emphasized on dynamics, more than it is being emphasized on when we talk about kinematics. Now, like I said, under kinematics, we are going to see the equations of motion. It's under kinematic that we will see the equations of motion, and other subtopics like projectile, and then the rest of them. But under dynamics, we are going to see the law of motion. We will leave it for the next service. We will talk about the law of motion in the next class. So this is, we see the law of motion, and the law of motion talks about the forces that causes the body to move and their effect on the body that is moving. So before that, let's look at the equations of motion. Now, basically, before going into the equations of motion, I would like us to define some terms in motion. There are some terms we need to define in motion, and they are simply starting from the basic. They are describing the properties of the body in movement or in motion. Now, the first thing we're going to look about is that we're going to look about we're going to talk about distance. I believe everybody here knows what distance is, or you've heard about distance. Simply, distance can be, we can define distance as length extended, or the extent of length, or will I say the length between two spaces is a distance. Now, length is conversely used to replace distance. Same as if distance and length are the same thing. So we have distance, and then the unit of distance is in meter. So distance is measured in meter. So we should remember this. Distance is measured in meter. And another thing again, another brother that we also have in motion that resembles distance is displacement. Displacement. Now, very, very important that they might also want to know whether you know the difference between these two, because they are similar. Because distance, the unit of measurement of distance is a meter, and then the symbol of distance is denoted as small letter s. Now, displacement is also measured in meter, and the symbol is also denoted with small letter s. Wow. What's now the difference between these two? Now, displacement is distance traveled in a specific direction. That means distance is just telling us about how far an extent went, but displacement is the distance in a vector field. Now, when we mean a vector field and a scalar field tells us how the magnitude of an extent or the magnitude of an occurrence, but the vector field tells us the magnitude of the occurrence and the direction of the occurrence. That means in the vector field, we are talking about how a body moves and in the direction or what direction did that body move. Now, what's the difference between the scalar field and the vector field? The scalar field is only used to tell us the quantity, but the vector field is more specific about direction. Now, for example, you can never be able to use the information given to you about the distance of a particle to find where it is. For example, somebody gives you an information that Nanka is 50 km from a colloid. The truth is that if you run with that information, you can never find where Nanka is, because that is just a mere description of where Nanka is. But the truth is that when you are standing to where Nanka is, you can't find Nanka, because Nanka can either be north, Nanka can either be east, Nanka can either be west, Nanka can either be south. You need to find the direction. So to accurately find a definite location, you don't need a scalar information, you need a vector information. That is the information that will give you the magnitude and also the direction of where you need. So when somebody says Nanka is, let's say 45 or let's say 50 km north, 50 degrees east of a colloid. So what I just need to do is to find my vertices and find my compass to locate where is 56 or 45 degrees east of southeast of where I'm staying, and then I'll move in that direction for 45 kilometers and I'll find myself in Nanka. Are you seeing it now? It's easy. You can easily find the direction and the location of the particle with the vector information. Now, that is the difference between these two. Distance is scalar, displacement is vector. And then they have the same formula, they have the same unit, and they have the same symbol. But they operate in different fields. Now let's look at other, we have speed. Speed is also another agent we speak about in displacement and in motion. Now what's speed? Of course, speed, we know about speed. Speed is simple, the change in distance over time. Now when a body, okay, let's use the normal conversant formula. We know about this in our junior secondary and primary school. They tell us basically that speed is distance traveled over time. The truth is that speed is distance covered in a specific period of time. That is, we are trying to find the ratio of our distance, the ratio of covering distance. Now, that's what speed is. To tell us how fast a body can cover distance in a particular period of time. That's what speed is trying to tell you. So speed is trying to tell you that this thing can move as fast as this over a particular period of time. The speed between two bodies is telling us the difference between how fast. Let's emphasis on that word, how fast a body moves. That's what speed tells us. Like I said, that speed is distance traveled over time taken. Now the unit of distance, remember, the unit of distance is s, the symbol is s, and then the time is t, small letter t, and then the unit of s is meters, that is distance is meters, and time is in seconds. So our unit is what? Meter per second. So the unit of speed is meter per second. Now let's look at another quantity. Let's look at acceleration. Now, before moving to acceleration, let's look at a photocopy of speed. Let's look at velocity. Now the same way distance and displacement are related, the same way speed and velocity are related. Now, for velocity, velocity is displacement over time. That is displacement over time. That means telling us that speed and velocity are the same thing. The only difference is that displacement, there is direction, distance, there is no direction. So it means that velocity is the speed in a vector field. So let's continue. So they can ask you question and then they might not give you direction, but they tell you that it is velocity. Just know that you are walking in a vector field. Some questions they will give you velocity, find velocity, and then you're waiting for them to give you direction. They will not give you direction. Just have your mind or know that yes, you are working in a vector field. Because if you are not working in a vector field, they will ask you for speed and not velocity. Okay, now displacement over time, remember, they have the same unit, the same symbol, and then the same unit, also meter per second. And then let's speed up into the next thing we're going to look at is acceleration. Now, what is acceleration? Now, acceleration is simple. Acceleration is the increase in velocity over time. What do I mean? Okay, we have speed, we have velocity, and then this is acceleration. Now, some people say that acceleration is the change in velocity over time, but I seem not to agree with that notion, because if we say that acceleration is the change, change can either be by increase or decrease. So something moving up is changing, something going down is changing. So acceleration must be specific, not just change in velocity, but an increase in velocity. Now, there's this thing that will I say, if you are somebody that is an automobile rider, you will find out that for your body to move more faster. Remember I said when we talk about speed, we talk about how fast. Now, when we talk about acceleration, we talk how faster. So if you want to move, you are moving fast, but you want to move more faster, there's something you must do. A body that is moving fast cannot just move more faster without doing something. For a body that is moving fast to move more faster, there must be an agent, and that agent is called acceleration. For a body that is moving fast to move more faster now, the body must accelerate. Now, acceleration is now what causes that body to increase in velocity, and of course, time is taken for that to happen. So, acceleration is just an increase in velocity over time. So, we have acceleration as saying we have velocity over time, and velocity we have it as meter per second divided by seconds, and then our unit of acceleration is meter per second squared. Oh yes. And then the last thing we're going to talk about under this equation of motion, we're going to talk about retardation. Now, what is retardation? Of course, like I said acceleration is not just change in velocity but an increase in velocity. Now, retardation is the opposite of acceleration. It tells us that a body increases velocity to speed up. What deceleration is when the body is reducing velocity. Now, the body that moves starts from rest or from uniform motion. So, the body that is moving can either start from rest or from uniform motion. So, when a body starts from rest, it increases in velocity, increases, and then increases, but a body that is moving will definitely come to stop. Now, for a body to come to stop, it didn't just fly from the maximum speed to zero. Of course, for a body to stop, it will first of all have to decrease. It's going to have to give up those acceleration it has accumulated. All those speed it has zoomed up, to begin to reduce them, and it will reduce, and get to zero before it stops. That phenomenon of decreasing the velocity before a final halt to that particular automobile or that particular body is what we call retardation. So, retardation is definitely called negative acceleration. So it seems as if the body is not moving faster, it's getting slower. If you want to do an experiment, if you are running with high speed, try and stop immediately. Is it possible? You are running with full speed and you determine to just stop at that particular point. Of course, you won't be able to do that. You can try it, but I bet you will enjoy yourself because there will be a negative feedback. There will be a reverse action that is trying to act against that force, causing a torque that will make you to fall off track. So that's why a body will have to retardate before the body will stop. Now the formula for this is the same thing with the formula for acceleration. The only difference is that this guy has minus attached to it. So if we have acceleration is equals to 5, your retardation is going to be equals to minus 5. And then nothing different between the both of them. They have the same unit, the same everything, but just different sign because their movement is opposite. This one is increasing, this one is decreasing. Oh yes. Now we are done with understanding the concept and every possible little definition on motion. And then let's look at a little idea of the idea of uniform and uniform velocity and let's look at uniform velocity. There is a term, we see them talking about uniform velocity, uniform acceleration, and so on and so forth. Now, uniform is constant. Now, when you hear uniform, it means that there is an equal movement in equal time interval. So when you hear uniform velocity, it means that, of course, velocity is velocity is distance. Velocity is displacement over time. So when the body displaces with equal time interval, or when the body displaces with the same range or the same distance with an equal time interval, that particular body is said to cover what we call, or move in what we call a uniform velocity. Let's say, for example, I'll try to use a diagram to explain this. Now look at what we mean by uniform velocity. Let's say the body is starting from here. This is distance, and this is 5 meters, this is 0, and then we have 2 seconds, 5 seconds, or 4 seconds. Now look at this. There is a graph reading now. We have a graph reading going like this, and then coming down. Let's look at this diagram. What does it mean? Now look at this diagram. This body is starting from here now, and then it is moving with a constant speed. There is no acceleration. It is moving covering 5 meters at what? At 2 seconds. There is no increase in velocity. It is moving with a uniform. So you find out that there is no increase in the distance is not increasing. There is no increase in the distance. Sorry, there is no increase in the velocity. By the way, there is a uniform. You see, the body is moving at a constant speed. So there is no. Now, what JAMB can ask you, at what point is a body said to cover uniform acceleration? The best definition for that is that a body is said to cover uniform velocity. Sorry, not uniform acceleration. A body is said to cover uniform velocity when there is no acceleration at all. Whenever there is no acceleration or retardation on the body in motion, that body is in uniform velocity. The body is not increasing or decreasing, moving with a constant velocity. That particular motion is called a uniform velocity. Now, we also have what we call uniform acceleration. Now, what is uniform acceleration? What is uniform acceleration? Now, uniform acceleration is simple. When a body is increasing at a particular pace, increasing with a little change in velocity over a small range of interval, no matter how small that time interval is, that particular range is what we call uniform acceleration. Like, for example, a body can just, let's say you are accelerating at 5 meters per second square, and you use that particular acceleration to move for 30 minutes. So you are increasing, the body is increasing constantly at 5 meters per second square. So every 5 meters, the body will cover, let's say, 1 second. Are you seeing it now? Every 5 meters, the body will cover. Every 1 second, the body is going to increase by 5 meters. So, and it is moving constantly. That particular movement is what we call uniform acceleration. Now, this particular part of the graph is what we use to denote this place is uniform acceleration. So if you see it in your graph, this place is uniform acceleration. It is used to denote uniform acceleration. You can ask it also in JAMB. And then this place is used to denote uniform velocity. This place is used to denote uniform velocity. And then this side is used to denote uniform retardation. Uniform retardation. Okay, I think we're done with terms. Then let's move into the equations of motion, and then we'll tie it. Now, equations of motion are simple. Equations of motion are simple. There's nothing more on equation of motion. It's just that they are formulas derived from the definitions of motions that we said earlier, and then we are able to find a mathematical format that can aid us in answering most questions, many questions on motion or questions of motion. Now let's look at the basic 4 equations of motion that we have. Basically we have 3, and then the last one is also, we can add the last one. Let's go with the basic 3 we have first. We have the V is equals to u plus at. We have that s is equals to ut plus half at squared. And then we also have that v squared is equals to u squared plus 2ax. And then the last one, we can try to add it, and u plus v over 2 multiplied by t. Okay, now remember that v is used as your final velocity. It's used to represent your final velocity. Your final velocity, that is the final velocity. This is the initial velocity. The velocity the body started with is called the initial velocity, while the velocity the body ended with is called the final velocity. So this is the initial velocity, and then our a represents the acceleration, and then our s is, of course, distance, and then t is time. And these are the parameters, or the parameters that we use, for the equations of motion. And then, okay, yes, everything is on the board. Final velocity, initial velocity, acceleration, distance, and time. Now, with these four equations on the board, you can be able to answer any question that is given to you under linear motion. Now, any question thrown to you under linear motion, you try to find a formula that will fit the question. Once you find a formula that will fit the question, you input the parameters inside the equation, then you get your right answer. Let's take one or two questions, and then you can also ask other questions in the comment section below. If you have a question, you can comment in the section question below. Maybe we have a time, because there are many more questions on that equations of motion. You can have a session whereby we just take like more questions on equation of motion. But for now, we'll just take two, and then we'll continue. Now let's look at this question. You have a question like this. You have a body at rest accelerates, or less, a body at rest accelerates accelerated uniformly at 5 meters per second squared for 5 seconds. Calculate the final velocity. Calculate the final velocity of the body. We have this kind of beautiful question. We have to solve it. The body at rest accelerates uniformly at 5 meters per second squared for 5 seconds. Calculate the final velocity. Now, whenever you are asked a question on motion, the first thing you should do is to bring out your parameters at all time. Try to bring out all the information. Try to, first of all, decode the secret or decode the information given to you in the question. Now, inside the questions lies clues that will give you the answer. Find those clues, bring them down, then find the equations, input those clues in the equation, then you get your final answer. And the first thing I've seen is reading the sentence and trying to find understanding from the sentence. A body at rest. Now, a body at rest, whenever you hear a body at rest in motion, it's not to be neglected. Because, oh yes, when a body is moving from rest, a body at rest, when a body moves from rest, we said or we know that a body or every body has a constant velocity. For the fact that the idea of constant, the intermolecular forces in our body, that we know that the molecules in the body are in a constant state of rapid motion. We ascertain that even the body at rest has a velocity, but the velocity at that particular point is set to be zero. That means When the body is not moving, it has velocity, and that velocity is, the velocity of the body is 0. It is not start to count, it's 0. But when the body starts to move, the velocity starts to increase. So since the velocity we said velocity is trying to, velocity can be likened with speed. Let's use the word speed. When the body is not moving, it does not have speed, but it starts moving with speed. It begins to come to play. Now, for a body to accelerate from rest, tells us that that particular state of rest has a velocity, has a speed. But at that particular point, at rest, that particular speed is 0. Okay, now, at rest, a body at rest accelerated uniformly. So the first information is that my initial velocity was given to me in that person, and the value is 0 meters per second. And then the next thing they say, it accelerated uniformly at 5 meters per second squared. The acceleration was given to me as 5 meters per second squared. And then the next thing that was given here was that for 5 seconds. Now the time was also given 5 seconds. Now they gave us a simple question to actually. They said calculate the final velocity. So V was the only man that was not given the question. It was the unknown. The V was the unknown. So the V was the unknown. Now, how do we solve for V? We're going to check the equations of motion we have. Oh, actually correct. Let me write them out again in speed. So okay, now these are the equations that we have. Now if you look at the board, we are trying to see how or each of these equations, which of them can be able to accompany or can be able to accept all these parameters. If we look at this equation will not help because it will not help us because there is distance here. There is no distance here. So this equation will not help. This equation will not help because there is distance here. There is no distance here. This equation will not help because there is distance here. There is distance here, there is no distance here. The only equation that can help us out is this man. Because this man does not have to do with this. So bringing out that equation, we have that V is equals to U plus 80. Then putting it inside the equation, we have that our V is equals to, our U was 0 or is 0, and our acceleration is 5, and then total time given was 5. Is 5, sorry. So V is equals to 0 plus 5 times 5 is 25. Therefore, our final velocity is 25 meters per second. So now, we're going to stop here. I believe we've treated many things on equations of motion. The only thing we'll do is I will find another class. You can be able, or then when we begin to talk about the laws of motion, we'll also touch some questions on equations of motion before we enter the laws of motion. So this class, thank you for the class. Those are followed online. Thank you very much.
Thank you very much, sir. All right, we will have another section of this motion, which will basically be on calculation. You know, we have done this, and Professor have done justice to that. So the other set of that class is waiting for us. You have a question on JAMB, drop it in the comment section. We're going to attend to it in no distant time. Thank you very much for watching, and see you soon.